Hi, y'all. It's me again. My son's over there.
Hi.
Yeah, there's Connor saying hi, which you probably can't hear him because he doesn't have a microphone. Um, this will be the next to last lecture for test number 2, and this one is about capacitors in series and parallel. And I will get the PowerPoint loaded up and ready to go, and we will take a look at this. All right. Okay, so what we have here is a couple of capacitors in parallel. So we've got a couple of capacitors in parallel. And the question I have is, well, how exactly do we handle this? We know how to handle resistors in parallel. We can remember that our resistor formula is what? 1 over R total is equal to 1 over R1 plus 1 over R2. And that's how we would handle resistors in parallel. Well, it turns out that capacitors are the exact opposite. If we've got capacitors in parallel, then their individual capacitances simply add up together. And that's because of the difference in the two equations that talk about the way charge responds to capacitors and the way charge responds to resistors. And let's see, if we recall from chapter 17, charge is equal to capacitance times voltage. So if we've got some capacitor storing charge, then and we know it's the potential difference across the capacitor, then the amount of charge it's going to store is Q is equal to CV. On the other hand, if we've got voltage across a resistor, then the amount of current that flows through the resistor is inversely proportional to the resistance. So you can see the role that charge kind of plays in both of these equations. We've got charges explicitly listed there for Q is equal to CV. And then we remember that current is equal to charge over time. So in our Q is equal to CV equation, Q is proportional to C. Q is proportional to capacitance. In our V is equal to IR equation, charge there is inversely proportional to resistance. And that's why we've got this difference between exactly how we handle resistors in parallel versus how we handle capacitors in parallel. All right, so it turns out that the equations for figuring out total capacitance are exactly opposite of what they are for figuring out total resistance. All right, so once again, there it is. Capacitance, total capacitance for parallel combination is equal to C1 plus C2 plus C3. We can compare the voltage across C1 to the voltage across C2. Well, those two capacitors are on parallel branches, and as a result, the voltage has to be the same across each branch. All right, well, what about charge? We know if we had current, and we've got this split right there, that our current would split, and we would have the current coming into the junction is equal to the current coming out of the junction. Well, it's the same way for charge. Q into that junction is equal to Q1 plus Q2. All right, so the way that we treat voltages and charges is the same. It's just that, because of capacitance being directly proportional to charge and resistance being indirectly proportional, we get the exact opposite relationship for the two. Inversely proportional, that's what I meant, not indirectly, inversely. I'm not going to re-record this though, so you guys are stuck with it. All right, so that was capacitors in parallel. It should come as no surprise to you then that if we look at capacitors in series, what happens? Well, we get that 1 over capacitance relationship. We remember that if we had resistors in series, what would it be? Resistors in series is equal to R1 plus R2 plus R3, so on and so forth. Again, the way we treat these guys is just exactly opposite. Okay, that's great. If we think about the amount of charge that each one of these stores, well, if we thought about the amount of current going through resistors in series, then we know that the total current has got to be the same through both those resistors. In the same way, our total current or total charge that's stored by this this particular circuit, well, that's the amount of charge that's stored on capacitor 1. That's also the amount of charge that's stored on capacitor 2, which is it's a little bit confusing. Nevertheless, there it is, and that's the total charge that that gets stored. All right. Well, what about the voltages? How do they add up? Well, we start out with some voltage. We start out with some voltage right there, and some of that voltage is going to get used up across capacitor 2. Some of it's going to get used up across capacitor 1, and as a result, our total voltage is equal to the voltage across 1 plus the voltage across 2. At any rate, we get that relationship right there for capacitors in series. All right, let's do an example problem real quick. So here we've got 4 different capacitors, and we're given the values of the capacitances, and we're asked to find the total capacitance of this particular combination. So in the same way we did with resistors, the process here is to identify simple series and simple parallel combinations of capacitors. So right away I can look at maybe C2 and C3 there. Oh, I drew with the wrong thing. I can look at C2 and C3 there, and I can say, oh, those right there, those are in series. So I can say that, let's see, my equivalent capacitance of those two is going to be 1 over C2 plus 1 over C3. And then when I plug in my values, this is 1 over 40. I'm going to drop the units, plus 1 over 80. And if I figure out what C sub A is from that, I get that C sub A is equal to about 26.7 picofarads. Okay, great, 26.7 picofarads. Well, what's next? Next is, the same thing as we've been doing in the past. It's just redrawing here our schematic. I've got C1, I've got CA, I've got C4. C4. Yeah, okay, I'm a child. Okay. So C1 and C4, or CA and C4 there. CA and C4 are in parallel with each other. Oh my word, what did I do? Stop that. Don't do that ever again. What? I just did that again. Stop it. It's bad. CA and C4 are in parallel with each other. And so as a result, I can just figure out their equivalent capacitance. Okay. They're just simply going to add together. That's 26.7 picofarads plus 13.3 picofarads. That, I guess this was supposed to be a nano. That gives me 40 nanofarads. Sorry, nano, not pico. Okay. All right. So what would my next step be? Well, my next step would be to redraw. Okay. What's going on here? Making lots of little dots. Okay, erase all ink on slide. Okay. Now back to this. Okay, draw there. Train wreck, sorry. So my next step would be to redraw. There we go. This is C1 there. This is CB right there. These guys are in series with each other. So as a result, I'm going to use my series formula for adding capacitances together, 1 over C1 plus 1 over CB. So 1 over CT is going to be equal to 1 over C1 was 20 nanofarads. CB was 40 nanofarads. And when I figure out CT, I end up with the result that CT is 13.3 nanofarads. So my equivalent capacitance of this particular combination of capacitors is 13.3 nanofarads. Sorry, guys, I know that was a little bit rough, but I hope I got the point across. All right, and there's one more example problem I want to do here. In this one, we've got a couple capacitors connected in parallel with one another, and they've got some kind of power supply that's allowing charge to be stored on those two capacitors. We're told that we want to store a total combined energy of 6.75 joules, and we're asked, well, if we want to store that total energy, then what voltage, what potential difference do we need to attach our two capacitors to? So there's our question. All right, let's see if we can draw this. It's capacitor 1, capacitor 2. They're in parallel and they are connected to a power supply. So C1, C2, BT. All right, yeah, you might imagine that the first step that I would take is probably to figure out what my total capacitance is for this particular circuit. So those two capacitors are in parallel. I'm going to use my formula for how capacitors in parallel add together. That's just C1 plus C2. I get 600 microfarads out of this. All right, awesome. So I've got that total capacitance, and maybe I could redraw. That's fine. Make sure my two plates there are very different lengths. There's my equivalent capacitance. Redraw there, but we still got the question, well, what's my voltage? And in order to figure this out, I have to go all the way back to chapter 17, back to like a week before break, something like that, and recall how energy, recall the equations for stored energy on a capacitor. One of those equations was energy is equal to 1/2 CV squared. I've got the energy. The energy is right up there. I've got the capacitance. Okay, the capacitance is right there. So as a result, I can figure out my voltage. So let's just plug this in real quick. 6.75 joules is equal to 1/2 times 300, and this is micro, so that's 10 to the negative 6 farads times V squared. Let's see, I got a, whoops, no, it's supposed to be an eraser. There we go. Times V squared. All right, I can solve for V here. Let's see, and when I do that, I get out that my voltage is 150 volts. All right, thank you very much, guys.